Now, our second talk will be by Simona Olmi. She currently holds a starting research position in the math neuro team at Inria, Sophia, Antipolis, Méditerranée Research Center in France. And she's going to talk about an exact neural mass model for synaptic-based working memory. So Simona, if you share your screen, great.
Okay, do you hear me? Is everything okay?
Yes, everything
okay,
works. Yeah.
Perfect. No, because, okay, let's, good morning. And in this talk, I will try to present you a new exact neural mass models that we have developed for synaptic-based working memory. As I think all of you know, working memory describes the capability to memorize and access and manipulate information that are obtained through stimulation, even though the stimulus is not anymore present. So in this framework, we try to develop a new neural mass model that is able to reproduce exactly the dynamics of heterogeneous Python neural network that are encompassing realistic cellular mechanisms for short-term plasticity. So in particular, in the rest of the talk, I will try to touch the following topics. So I will describe and detail the agreement between the microscopic and the macroscopic dynamics, and I will discuss about memory loading, maintenance, and rehearsal via the persistent activity and the other phenomenon which is related to population burst. I will try to discuss about the competition about working memory items, and I will try to give you a flavor of the role played by different frequency bands in the working memory activity, trying to understand which is the dependence of memory capacity on the presentation rate. I imagine that the first question that arises in your heads in this moment is, why do we need another neural mass model in order to describe this kind of phenomenon, since there are a lot of heuristic neural mass models? So let me say the message of this talk, the take-home message, is that we can have some benefits from this model because I'm going to show you that we combined the exact neural mass that comes from recent findings in in-field theory with the well-established synaptic plasticity, short-term plasticity model developed by Zodix, Matram, and co-authors. And in this framework, I can affirm that our model is really powerful because, as I will try to show you in the following slides, it gives the one-to-one correspondence between the network, so the microscopic dynamics and the mean field evolution, so the macroscopic dynamics of firing rate, mean membrane potential, and synaptic variables, thus allowing to simulate very large networks. And in contrast to the well-known heuristic neural mass models that are usually used, it will allow to show subterranean integration that you will see are very important when retaining and loading the items. And most importantly, it gives us the mean membrane potential, and so it allows to describe the dynamics of evolution of the mean membrane potential that we usually can relate to experimental signals like EEG and so on. So let's go on. The microscopic dynamics, so the neuronal dynamics is described by a network of quadratic integrated empire neurons. For this kind of networks, in 2015, Monbreo, Pasot, and Roxin have developed an exact macroscopic description, exact neural mass models that takes into account the evolution of the instantaneous firing rate of the network and the mean membrane potential. Together with this, we will take into account the macroscopic short-term plasticity developed by Zodix and co-authors in 1998, where are taken into account the evolution of the depression and the facilitation. In this figure, I've taken into account the interaction and the role of the passion and facilitation between two neurons, but this can be easily extended to the interaction between two populations. So we come to an exact neural mass model with short-term plasticity for a single population. So that takes into account the evolution of the instantaneous firing rate and the membrane potential, and the evolution of the synaptic resource X and the utilization factor U that are coupled back, so the short-term plasticity is coupled to the dynamics of the network here in the equation for the membrane potential. So this is the basic model for one population that we can extend to a multi-population. And the easiest kind of architectures that we have considered is this one that allows to take into account the memorization and loading of two items, because it is composed by two excitatory populations that are connected to the same inhibitory. In particular, each excitatory population displays short-term plasticity and codes from one item, and it can be stimulated by a stimulation current ES, while there is a common background EB that touches all the populations in the network. So if we start investigating what is going on, we will see that it is possible to observe memory loading and also memory competition just using two excitations. In particular, we have performed an experiment which is inspired by the one that has been shown by Mongillo and co-authors in 2008. And in particular, we tried to see if it is possible to maintain and to load items in one of the two populations by simply varying the population background. So if it is possible to have some memory maintenance with different dynamical regimes. And we see that it is possible to have maintenance through a mechanism that is related to population burst, as you can see here, and with persistent state. So for both the situations that are obtained by stimulating just one population, we see that there is a perfect agreement between what happens at the network dynamics, as you can see in this paragraph, and what happens at the level of the mean field dynamics. In particular, the features that emerge in this kind of memory loading and maintenance is that we observe a delta activity that is related to the excitatory population burst and the beta band activity that is due to the fast inhibitory collective oscillations. So the working memory that we observe is due to a ping-like mechanisms that is driven by the inhibitory beta band. In addition to this neural mass model allows also for a competition between memory items, as you can see here, which is called usually memory juggling. In particular, if we stimulate also the second population after the first one, we see that also the second population starts giving rise to a population burst, and so there is a memory, two items are memorized and compete, thus giving rise to memory juggling. So the entire phenomenon of memory juggling can be seen more in details by looking at the phase diagram, where we take into account what happens if we vary the amplitude of the stimulations and the duration of the stimulation. In particular, if we start from the situation of population burst, we see that it's possible to obtain for small amplitudes and for small duration just the retaining of item 1, so the item that has been memorized by the first population. Then for intermediate parameter values, we see that a frequent outcome is the coexistence between the two memory items, which means that we have juggling. And finally, just for sufficient long perturbation and intermediate amplitudes, we observe that item 2, so the item in the second population, prevails and it is memorized. This is completely different from what we see if we start from the situation where we have persistent state, because in this state we don't observe memory competitions, And the minimal perturbation amplitude, you can see needed to observe an item switching is now larger than other case. Another difference with respect to the other setup is that there exists a narrow stripe where item 2 can be selected, and then we observe more or less the same behavior for intermediate amplitudes and large durations. So things can be more complex if we use a bigger topology. In this case, we have considered a 7-item network where we have 7 excitatory populations that are coupled to one inhibitory. In this case, if we present successive items to successive populations, we obtain some delta activity related to the moment where we load the dynamics, but we see, looking at the spectrogram, that there is a dominant signal which is due to the resonance between the delta activity and the beta band due to the presence of the inhibition. Of course, here we have presented the items at a certain rate. You see first item presented to the first, second item presented to the third population, and yeah, I see, and third item presented to the third population. If we do an extended analysis and we see what happens if we vary the presentation rate, we see that we have an interval of a window of frequency presentation where there is an optimal response of the network. So we see that we have a maximal capacity that is equal to 5, but while we see that for slow population, just the last items that are presented are retrieved and thus memorized, while for a fast presentation rate, we see that the first and the last items that are presented are memorized. So I want to conclude and give the time for questions. Just say that I tried to, with this talk, I tried to convince you that this population model is good to be used and can give a lot of, can have a lot of success, since it reproduces the macroscopic dynamics of the networks in terms of the firing rate and mean membrane potential, but is able to reproduce a lot of features that can be seen in the experiment, like the role played by different frequency bands and memory competition among the items. Thanks a lot.
Thank you very much, Simona. So if you have questions, put them in the Q&A window. So maybe I'll start with one question. So you showed that you, in this new mass model, you have several excitatory populations.
Yeah.
So right now it's also, people are starting to look into the different functions of different types of inhibitory neurons. So I assume that having different populations of interneurons with different characteristics would also be possible with your new model, right?
Yeah, of course. In the sense, the idea was to let me try to come back. The idea was to use a single inhibitory setup to simplify the presentation, to simplify also the investigation analysis. But of course, what is clear is that you can couple in different ways the you are free to use the type of topology that you want to use. And what I expect is that then all the role played by the population will grow, in the sense that the inhibitory population is a sort of clock, and in the sense that you really see, if you look at the spectrum, for example, that the inhibition is really interacted, the inhibitory population is really interacted with the other ones, and you have a resonance effect that allows you to have a bigger signal in the beta gamma frequency bands. So all the fast frequency activity, the fast frequency band is enhanced due to the inhibition, and this will be enhanced if we use more inhibitory populations with respect to just one, imagine.
Okay, thank you. So we still have time, so maybe I'll ask another more technical question. So how much do you gain by this low-dimensional description? So how much faster is it if you simulate that compared to?
You have to imagine that this neural mass model is the infinite size limit of a network. So in principle, you are simulating a network on an infinite size. And you can simulate it very easily in few seconds, in the sense from a computational point of view, the analysis is very fast, while allowing you to add more and more biological characteristics to somehow to the network.
Okay, so thanks again, Simona.
Thanks.
And we'll move on to our next speaker, last speaker.